let's talk about gases. So we're in chapter 5 now. The gas chapter, a lot of this will be reviewed, but there's a few topics within the chapter that will be new. So some students, they ask me, when are we going to get to something new? Well, we haven't gotten to a lot of new things yet, but you can tell how the depth is maybe a little more right now. And also in chapter 5, though, we do have a couple new concepts. So, okay. So if I were to ask you, why are gases important? I was like asking that question, why is it important? Like, why does it matter? Well, I mentioned the hydrogen sulfide poisoning incident on the dock, but here's another question related to this. Do you know anyone who requires oxygen at home? Anyone have like an elder at home, grandparent, parent who needs to have oxygen delivered to their house? Well, oxygen's a gas, right? So that's really important. Okay. Some babies are born oxygen deprived. Here's a picture of a baby oxygen deprived, not doing so great, but here she is today. Actually, not today, a couple of years ago, but that's my daughter. So I figured I'd just share a little good feeling story. You know, when my daughter was born, she was born in respiratory distress. They believe she swallowed some meconium during birth. If you don't know what meconium is, it's when the baby poops itself while still in the womb, and then as the baby's being delivered, it was a rough delivery, but they believe some of that bacteria in the meconium got in her lungs and caused her to be oxygen deprived. So she spent 10 days in the NICU, neonatal intensive care unit, NICU, and they put her in a little incubator kind of compartment. She had a little bit of jaundice as well, and they had a webcam on her, so even from home I could take a look and see if she was there. Occasionally they would take her out because after all you have to feed them and change them, and whenever they would take her out, I'd get a phone call from a relative, hey, they took her out, where is she? Where is she? Relax, she's, like they do have to bathe her and feed her, so yeah, she's missing, somebody walked off with her already, So obviously I was at the hospital every day, but it's like, you can't be there all day long, so, or all night, you gotta sleep. So anyway, so that was when she was a newborn. This is age 3 or so now. She's 5. She started kindergarten a couple weeks back, so she's doing great. And she has a little brother now that she can pick on all the time. So oxygen's important. When I was in the NICU, I was asking one of the nurses how they monitor the oxygen levels. You can see in this picture, they've got a little, actually, I guess you can't see it too well. They had a little, oh here it is. They have a little blue clamp there. Sometimes they attach it to the fingers, sometimes they attach it to the toes. But it's a little red clamp or a little clamp, and it sends a red light through the skin. And what they do is they look at the reflection of that red light back out from the skin, back through a fiber optic, and the extent to that reflection represents how much light is being absorbed by the hemoglobin molecules in the body, and how much that light is reflected depends on how much oxygen is being bound by the hemoglobin. So they can monitor oxygen blood saturation with that device. And the nurse didn't know how it worked, but I remember when I was taking an instrumentation course in college, I read the paper where they developed the technology to do that. And so then I got to see it in action for my daughter, so I was like, that's so awesome, I'm just sitting in the hospital. So now it's used in all hospitals, and it's great, works great. So oxygen, obviously, probably maybe the most important gas to us, right? We can't live without oxygen. Here's another question that I asked when I was doing a baby CPR class. Why does CPR work? I always thought when we breathe into someone's mouth doing CPR, aren't we breathing in carbon dioxide into their lungs, not oxygen? Why why are we breathing in CO2 that somebody's not going to help them? Turns out that all the air that we breathe, we don't use all the oxygen, we actually breathe back out some oxygen. Maybe as much as 60% of our exhaling is still oxygen. And so it's better to give somebody some oxygen than no oxygen, right? Okay, and then of course, with my atmospheric chemistry background, pollutants are in our atmosphere. We live in a toxic soup of gases, especially if you look out, drive up Harbor, up to Bass and Cherry. Okay, there's a really nice restaurant at the top of the hill off of Bass and Cherry called the Summit House. That's where I had my wedding reception. When you go up on top of that hill, and you say, yeah, let's go for a nice, beautiful walk on the hill. It's beautiful. It's kind of wildlife up there, deers and insects. And then you look over the city, and what do you see? Smog. You see brown, like brown smog, right? You know, nitric oxides are the main source of that brown soup-looking color. And it's hard to believe that we live in that. But when we're in it, we don't see it. It looks homogeneous to us. Okay, but when you're standing out away from it, you're just amazed that we actually live in it. So all of that is driven by photochemical smog. The sunlight drives the chemistry, and you get this chain reaction of various pollutants that form as a result of the oxidation of incompletely combusted hydrocarbons released into the atmosphere. So we oxidize hydrocarbons, fuel in our cars, but that's not efficient. And there's a lot of pollutants that come from our tailpipes. And so what's left goes out of the tailpipes into the atmosphere, and the sunlight finishes the job and drives this further oxidation of hydrocarbons. And you get really, really nasty polar organics that will form particulate matter in the atmosphere. That particulate matter, PM 2.5 micrometers versus PM 10, particulate matter 10 micrometers in diameter. And that particulate matter is what gets lodged in our lungs, in the alveoli of our lungs, and leads to lung problems. So yeah, it sounds really depressing. They've actually done studies where they show within 500 feet of freeways, the air quality is increasingly bad. As you get close to freeways. So if you live close to a freeway, I'm sorry. I'm just breaking bad news to you right now. It's a different kind of breaking bad. I'm breaking bad news to you. Anyhow, that was pretty good. Anyway, I just rolled out. Breaking bad news to somebody who's not good. Okay. So obviously air problems as well as life-saving gases. Gases are always a mixed bag, and then there's a whole history of gases too. There's the guy who developed a process to produce ammonia on a mass scale, ammonia vapor. That ammonia is used in fertilizers. It's why we can grow lots and lots of crops. But that same guy was a Nazi, and responsible for the deaths of many lives in warfare using chemical warfare agents. So just like that guy, it's a whole, gases are a mixed bag. Some are great, some others not so great. Okay, so properties of gases mainly include very non-dense matter. Okay, gases, the molecules are far apart. They're moving in random motion in the air. You can compress gases into a more dense sample because gases in general have low density. Okay, so what causes pressure? Okay, other than the fact that you have an exam next week, what causes pressure? No pressure. So what causes gas pressure basically is what you don't realize it, but what you're feeling is collisions on your body by the atmosphere. That's what causes causing pressure. But we're so used to it that we don't really notice it. So force is pressure is a force divided by a unit area. If you decrease the area, you increase the pressure. So it's like saying if we shrink the volume of a container, but we don't decrease the number of particles in that container, we're going to increase the pressure inside that chamber, right? You're decreasing the surface area. Okay, now one way that they measure pressure in the atmosphere is using barometric pressure or using a barometer. So you know how sometimes you get the weatherman, my favorite weatherman is Dallas Raines. You ever heard of Dallas Raines? Like the name is perfect, right? He's Dallas, like in Texas, and it rains in Texas sometimes. So Dallas Raines, and so he's always, I like watching his newscasts because he's really excited about weather, and sometimes he gets technical with high pressure, low pressure. But sometimes what he'll say is, when we're having a heat wave, he's like, it's bright and sunny and the mercury's rising, he says like that. So what does he mean by the mercury rising? What he's talking about is as a barometer, and if you have a pool of mercury, and if the atmospheric pressure starts increasing as we get a heat wave that comes in, high pressure dome builds in, as they say, and that high pressure pushes the mercury down, and the mercury will then flow up a capillary up to a certain distance, okay, and the rest of the capillary is under a vacuum. So that distance that it travels is dependent upon the atmospheric pressure. So when he says the mercury is rising, that's what he's talking about. Heat wave comes in, atmospheric pressure increases, pushes the mercury rising up through a capillary. At normal atmospheric conditions, that distance is 760 millimeters up the capillary. And so that's where the pressure of millimeter mercury units came from. Okay. Now, if you tried to do water up a column instead of mercury, you would need to have a column that rises up at least 34 feet high, which is sort of not very, I don't know, logistically feasible. Why does water go up 34 feet high, but mercury only goes up 760 millimeters? Which, I don't know, 760 millimeters, that's about 76 centimeters. 76 centimeters isn't that high, right? It's within the room here, certainly. Maybe my height, less, maybe less. So why not use water instead of mercury? Well, why does mercury rise only 76 centimeters? It's more dense, right? Mercury has a density of about 10.8 or so grams per cubic centimeter. Water, only 1 gram per cubic centimeter. So they want a more dense liquid. So mercury is ideal for measuring barometric pressure. The units that come from these processes, 1 atmosphere equals 760 millimeter, that's things you've seen before, I'm sure. 1 atmosphere is equal to 760 torr as well. When I was doing research in an atmospheric chemistry lab, I used torr a lot. And on gas tanks, they use PSI, pounds per square inch. It's approximately 14.7 psi for 1 atmosphere pressure. The Pascal used less in chemistry, maybe a little more in physics and in engineering applications. So these are just some common conversion ratios that you should be probably used to using at this point. When you go to the doctor or nurse and they take your blood pressure, what are the units of blood pressure? I got you again? All right. So ask a nurse or ask the medical assistant what the pressure of systolic pressure is or diastolic pressure, and they won't know. But I'll tell you right now, the units are millimeter mercury, right? So, and for systolic pressure, the normal range is 100 to 120 millimeter mercury. So when they're measuring blood pressure, which is a liquid pressure, they still use gas units, millimeter mercury. For the diastolic pressure, what do you think the typical range is? Well, if they give you your blood pressure, they say it's like 120 over 80 usually. So the normal range is 60 to 80. If you're having a pretty relaxed day, you might be as low as 100 over 60, I always love it when I get that low. It's like, yeah, okay, I'm still, still low. What's going on? How you doing? 100 over 60, right? Yeah. Whereas if you walk in, 150 over 100, huh? Like, yeah. All right, so All right, so those are the units of blood pressure. If you go to the eye doctor, the optometrist, and they measure your eyeball pressure with that, the air chute they do in your eye, they're looking at the signs of glaucoma. That's also millimeter mercury, and the optometrist won't know what the units are. Trust me, they just don't. They just care whatever gets it done. Okay, what is 475 millimeter mercury expressed in atmospheres? What would that be? You could do this without even doing the math, really. 475 millimeter mercury, there's 760 millimeter mercury in an atmosphere. So, is it 475 atmospheres? Definitely not. Is it an even larger number of atmospheres? No. It's got to be this one, right? So 760 is normal atmospheric pressure, so it has to be something less than 1 atmosphere for 475. So 475 divided by 760 would give you 0.65. The pressure in a tire is 2 atmospheres. What is this pressure in millimeter mercury? Again, you can do this in your head, probably, given the choices. So if 760 millimeter mercury is 1 atmosphere, what would 2 atmospheres be? And double that, right? So 1520. This is just basic, unit conversions of pressure. Okay. Gas pressure is measured oftentimes with something called a manometer. It's just a type of pressure gauge. Let's just take, for example, if the outside pressure is 765 millimeter mercury, so a little bit above normal atmospheric pressure. And let's just say this picture describes gas pressure. So the question becomes, what is the gas pressure inside this chamber, given that it's attached to a U-tube full of mercury, and the outside pressure comes out to the top of this tube, and it's 765 millimeter mercury out here. And the difference between these two levels on both sides of the tube, that difference is 125. What do you think the pressure inside this chamber is then? First question, is the pressure less or more inside the chamber relative to the outside? Is the air outside pushing down on the mercury more on this side or more on this side? More on the right. So the pressure outside is greater relative to the gas in the chamber here. How much less pressure is in here relative to the outside? Well, if you take this difference right here of 125 millimeters, okay, relative to the outside, what do you think the pressure then would be in here? 765 plus 125 or minus 125? Yeah, it'd be 640, right? It'd be minus 125. Okay, 640 millimeter mercury would be the pressure in the chamber. So P chamber, 640. Why do I have a decimal place there? Sig figs. Sig figs again? This just never go away. Just like cockroaches, they never go away. I'm telling you. Sig figs and nomenclature never goes away. Okay. That's why I say sig figs, nomenclature, the 2 cockroaches of chemistry. All right. So 765 minus 125, no numbers to the right of the decimal. So you put a decimal place ahead of that 0 to designate that there's still 3 sig figs there. Okay, what about the next picture? What do you think the pressure in the chamber is in that picture?
765 minus.
Yeah, some people are from 890. Okay, you'd be right. The 890. Why is it 890? Because now the pressure inside the chamber is 125 greater than the outside. All right, so it's 890 for the pressure of the chamber. So I just want to cover the basic gas laws, and we'll probably call it a lecture here. It boils down to this. If you decrease the volume of a gas, the pressure increases. It boils down to that. And that's why we call it Boyles' law. Okay? So what that inverse relationship can be written as, it can say, well, volume is proportional to 1 over the pressure. So this sign here, this little alpha sign, it means proportional to. And whenever you have a proportionality relationship, you have a constant of proportionality. And so now this proportional sign changes to volume is equal to some constant times 1 over P. And if you solve for that constant, you could say, well, pressure times volume is always constant. Okay, how does this work? Well, if I increase the pressure, the volume has to decrease. If the volume increases, the pressure has to decrease. So that factor, P times V, will stay constant. See what I'm saying? All right, so Boyles' law states that if volume increases, pressure decreases, and vice versa. So if the pressure is doubled, the volume is halved. If the pressure is cut in half, the volume is doubled. If the pressure is quadrupled, then the volume is cut by a quarter, or cut into a quarter. Okay. So if you say, then if a gas undergoes some change or gets compressed or expanded, and P times V is always constant, you can state this relationship. Okay, P1 times V1 being the initial conditions equals pressure times volume after the compression or expansion. So here's an example. A sample of gas has a volume of 5.71 liters at 56 torr. What's the pressure if the volume is equal to 1.35 liters? So what's happening? Is the volume increasing or decreasing? Yeah, the volume is increasing, so what would you expect to happen to that 56 torr? Would it go up from there or down from there? It would decrease, right? The volume is increasing, so the pressure is going to decrease. Okay, so what is my V1? So what is my initial volume? 5.71. 5.71, right? What is my P1? 56 torr. What is my V2? 1.35 liters. What is my P2? That's what it's asking us for. So solving for P2, we know that P1 times V1 is equal to P2 V2, so dividing V2 over. And so that gets us to 56 torr times 5.71 divided by 1.35 liters. Liters cancel, and you get some value in torr. Does the torr have to be in atmospheres here? For these problems, no. It just says, what's the new pressure? Now, if it says, what's the new pressure in atmospheres, then yeah, you have to convert it after. But it's just asking, what's the pressure? You can pick any pressure unit you want. So this is a really easy plug and chug, Chem 107 style kind of a problem. But I'm just introducing it here. So the answer would be 240. Did anyone happen to punch that number in? What did you get?
236.859.
236.859. So how did I get 240? Sig figs, right? 56 torr has only 2 sig figs in it. So 236, okay, how did I round that up to 240? So just reviewing, just a real quick review, 6 rounds up into 3 makes a 4, but you got to remember not to just leave it at 24, you got to remember it's still the same order of magnitude of 240. You just got to be careful. You're all pros at this now, but occasionally I see someone who forgets that they're a pro. So, all right. Okay, so 240. Now, Boyles' law is one of my favorite gas laws to talk about because I have a story about it. So I was on an airplane once flying from LAX to Tucson, Arizona. I got family out there. So I'm on this plane, and I see this lady sitting next to me. She has her daughter there, and I noticed that her potato chip bag was about to explode. And you can see it's really puffed out, right? You can see the picture. Why is the potato chip bag ready to explode? So she bought that bag in the terminal at LAX at sea level. All right, this is on the plane now. What's the pressure on the plane? So you may not have heard this while you're on a plane, but the pilot will usually say that they pressurize the plane to an elevation of about 10,000 feet. Now, they fly the plane up around 30,000 feet. Okay, that's the cruising elevation for the plane. But they'll pressurize the cabin pressure to about the same atmospheric pressure as what you would have at a mountain peak at 10,000 feet above sea level. So it's now the pressure is less outside than it was at sea level when she bought the bag. So now the pressure inside the bag, the gas inside that bag is still at atmospheric pressure, but the outside cabin pressure is much less than 1 atmosphere. And so that's why the bag is ready to explode. So I asked her to hold the bag, and let me take a picture of it. I cannot begin to tell you the look on her face when I first asked her if I could just take a picture of her bag. She thought I was the weirdest guy ever. and the fact that she had her daughter with her, she's probably thinking like creepy dude, get away from me, you know. And of course I explained to her at that point that I teach chemistry, and if I wanted to take the picture to illustrate a concept, you know. But and she calmed down after that. Thank goodness. And it was only an hour-long flight, so she only had to put up with me for an hour, so it was cool. It was during the daytime, it wasn't like it was at nighttime and she was trying to get sleep or something. So, yeah, it all worked out, but kind of a funny story though. I mean, it's a weird thing for someone to ask, right? Can I take a picture of your potato chip bag? Anyway, this is funny. Okay, oh, and when you travel, well, guess what? So I fly into Tucson. I forget, of course, to Ziploc bag any sunblock lotion or something, and I open up the sunblock when I get to my family's house there, and of course, what happens? It explodes. Like all the lotion comes squirting out because, again, at atmospheric pressure down here, we have about 1 atmosphere. Tucson is about 3,000 feet above sea level, and there's a noticeable difference in atmospheric pressure even from sea level up to 3,000 feet. And so if you're going to a higher elevation, just tamp down that lotion bottle so all the air just goes on top, and when you open it, you hear all the air kind of spew out at that point. So yeah, Boyles' law. As pressure goes down, volume goes up. Right, gas wants to expand out of the bag. It wants to expand out of the lotion bubble. All right. It boils down to that. Okay. Last concept, and then we'll end it there. So the next law. So there's Boyles' law, and there's Charles' law. What Charles' law basically says is, as you heat up a gas, the volume expands. That's more intuitive. It makes sense. So if you increase the temperature, double it, volume will double. Half the temperature, volume gets cut in half. And so forth. And again, here's this proportionality thing. Volume proportional to temperature. Now you have a constant of proportionality, and then if you solve for that constant by dividing T down here, you'll get this V over T. Okay, and that's how they get Charles' law in an equation form. They just take V1 over T1 equals V2 over T2. We'll go ahead and stop here, and then we'll take up this example tomorrow. So it's time to head upstairs.